Yes, okay, great. Then let's get started. So yeah, as Ole just said, so my name is Arno Förster, and you see here my email address. So if you have any questions I won't answer, or if right away, or if any question later, please feel free to reach out. So what I will be talking about today is a practical guide to GW-BSE and Sigma-functionals in the Amsterdam modeling suite. And that's, of course, let's say, a topic which is, let's say, very close to my heart because, well, that's the type of work I did during my PhD at SCM, and which I am continuing doing now at the moment. And I want to thank you all for joining. I'm very happy that so many of you are here. I know in Europe it's already quite late. In the US, you might have just woken up. So appreciate that all of you are here. All right, let's get started. What will I be talking about today? So I'll introduce Green's function. So that's kind of what we need to talk about GW-BSE. Let's say that's a language we will be using. But I don't want to be much way too theoretical. So yeah, I'll introduce a few basics, and then I will be very quickly going over to, let's say, GW-BSE in practice. Like, what can you do with it in your research? And then I will kind of give like a practically oriented example, kind of showing you what are the common pitfalls and how to overcome those pitfalls. And then in the very end, I will also talk about Sigma-functionals. So that's kind of like a little bit of an appendix, if you wish. But yeah, it's related because Sigma-functionals are also formulated, let's say, in the Green's function language. And I think those are great. So I want all of you to use them if you care about energetics. All right, let's dive right into it. So what's a Green's function? So at least in chemistry, I think Green's function are always a little bit mysterious, but the concept is actually quite simple. So you see here, can you see my cursor, my mouse moving? Can someone quickly tell me if you see it?
Yes, we can see it.
Okay, great. So then you see here on the top, you see the G. So G stands for Green's function, and by the way, also the G in GW stands for the Green's function. What the Green's function essentially does, it takes the ground state of an n-electron system, and it creates an electron at point x prime and t prime, where x, let's say, is real space and spin. And then it annihilates again at x and t. In other words, it basically just tracks the time evolution of a single electron. So that's, in principle, a simple object. So it's very low dimensional, but it's very complicated to calculate. However, what can we calculate efficiently? That's this quantity below, the so-called G0. G0 does exactly the same, but for that we assume a non-interacting hypothetical reference system. You, of course, might be familiar with cone-sham DFT, and it's exactly the same idea. So we basically create an electron in the non-interacting reference system and annihilate it later again. So that's G0, and that's, of course, something we can calculate very easily. We can calculate it easily, but it's also useless in practice because, of course, we are interested in our interacting reference system, in our interacting system, not in our reference system. So basically what G does, it kind of introduces all the interactions between the electrons. And of course, that is kind of like always in quantum chemistry, let's say, the elusive part we want to capture, and it's always notoriously difficult to describe. So in Green's function language, we have now the equation 2, that's kind of like the central equation behind all of this formalism, which basically tells us, give me a G0 and a quantity, the so-called self-energy sigma, which depends on G itself, and I give you the right exact G. You might have already guessed, the problem, of course, is now that we don't know the self-energy sigma, and we have to approximate it in practice. Sigma is dynamical, so it depends on time or frequency if you Fourier transform it. It's also non-Hermitian, but essentially it's just a mean field. All right, so how can we actually calculate the self-energy? So what we do in practice, we do perturbation theory. So we start from non-interacting reference system, and then order by order introduce interactions. So I indicated here on top that the self-energy depends on G, so that's the interacting G, and on the Coulomb potential, V Coulomb. And then we can expand the self-energy in powers of the electron-electron interaction. So at first order in the interaction, we get Hartree-Fock. So we have two terms, the Hartree term and the Fock term. Second order in the interaction, we'd also get two diagrams or two additional terms. I always like to say diagrams. So if I say diagrams, it just means term. And that's what we would typically call MP2. And then you can go on and on and on. As you all know, of course, the more complex these terms get, the more expensive to calculate they are. But that's essentially what we can do to calculate the self-energy. I want to draw an analogy to density functional theory, because of course we are all familiar with DFT. And the analogy is actually quickly drawn if you just say that you take the non-local Hermitian dynamical self-energy and replace it with a local, static, and Hermitian exchange correlation potential. And what then happens is the Dyson equation, I mean, that doesn't really change a lot. I mean, you get like a delta function in here. But what you can do, actually, you can show that this exactly can be rewritten as a Kohn-Sham equations. The solutions we are getting here are something what I would also call quasi-particles. I didn't introduce that term yet, I realize, I think. So a quasi-particle essentially is an electron, which is not only an electron, it also includes the interaction with its environment. I will come back to this later. So let's call it, let's say, a quasi-particle obeys a one electron-like equation, like the Kohn-Sham equation, but this one electron equation contains an effective potential. The solutions of these equations are quasi-particles. Unfortunately, these quasi-particles in DFT, they don't really correspond to anything physical. In DFT, what's physical is the density, but the quasi-particles, they're not physical. Well, in finite systems, the first ionization potential corresponds to minus the HOMO. So that is physical, but that's an exception. Now we also have Hartree-Fock theory, and that is actually also not so much different. So the only difference to Kohn-Sham DFT, formally, of course, only is that now our let's say our mean field operator is also non-local. Okay, but we get exactly the same thing. So the Dyson equation translates to the Hartree-Fock equations, and the solutions of the Hartree-Fock equations in principle correspond to ionization potentials and electron affinities, and therefore, let's say, to physical charge excitations. That's also known as Kopman theory. And actually, I will introduce the concept of screening later. GW can actually reduce to Hartree-Fock. Hartree-Fock is a very good approximation to GW for small molecules. I would also like to say it can, of course, be merged with DFT. You all know hybrid functionals, etc. All right. Okay, what does GW do now? GW is an approximation to so-called Hedin's equations. Hedin's equations are named after Lars Hedin, who introduced these equations in 1965 in a very famous paper. And Hedin had a very nice idea. He had the idea to replace the self-energy, which is the functional, remember, of G and V, by a functional which is now constructed from G and W. And what is W? The idea is, okay, we have quasi-particles. Quasi-particles behave like electrons, but not really. And surely, if these quasi-particles start interacting, they do not interact with each other like electrons. Well, they interact with each other like quasi-particles. So they include their mutual interactions, and in particular, they're shielded. So basically, quasi-particles have a weaker interaction, or like a weaker charge, let's say, than electrons. So their interaction is also weaker. Actually, this concept is also very familiar to many chemists. Actually, I remember in high school, we had like this teacher who told us that if you have like an atom and you take an electron in the valence of the atom, it doesn't experience the full charge of the core, but the charge of the core is actually screened by the presence of all the other electrons. And that's exactly screening. it doesn't experience a charge of the full core because the electron-electron interaction is screened. And also physicists know this since a long time, though there's theories of screening around since, I don't know, like 100 years maybe. So, and especially when you want to describe the electronic structure of metals, screening is a central quantity. So Hedin knew that, and he basically kind of formalized this idea by saying, well, I can turn my G naught into a G via the self-energy, and in the same way, I can turn my Coulomb potential into a shielded Coulomb potential via a new quantity, which is typically called polarizability. So Hedin was very modest, and in his paper, he also wrote in the abstract, there's not much new in principle in this paper. The emphasis is on the development of a numerical manageable approximation scheme. So yeah, he was apparently a very modest guy, and of course, as scientists, we always like to, well, sell our work well, but Hedin, well, he didn't feel like he had to do it, and I guess the quality of his work just spoke for itself. And what is also true is that indeed, this work is actually mostly famous for the numerically manageable approximation scheme he developed. Okay, let's show first a whole bunch of equations. So these are Hedin's equations. It's essentially just a set of 5 coupled equations. And you see on the right, basically, you can kind of self-consistently iterate them. And when you are done, well, then you found the exact Green's function of your system, which is great. However, obviously, in practice, impossible to do. Hedin basically managed to formulate these equations in a way that all of the difficulty, or most of the difficulty, let's say, is hidden in this quantity called gamma, the so-called vertex. That's the first equation. So basically, if you just eliminate this vertex, or not eliminate it, but approximate it with the first term, these are just delta functions, well, then you're good. And that's what Hedin did. So he basically was like, okay, let's remove that vertex. And what we get are only 4 equations, and that's exactly the GW approximation. So the GW approximation are now 4 coupled equations, which you can also solve self-consistently. We typically don't do that in practice. I will tell you later in detail what we are doing. But it has this Dyson equation for G. It has another Dyson-like equation for the screened or shielded interaction. And then we have these expressions for the kernel. So we have the self-energy, and that's just a single term. So the diagram looks a little bit like a hedgehog. I always like that one. And the polarizability is just a single bubble. So that's what we have. And that's really not much, actually, and it's quite easy to calculate. Before I tell you why this is actually a good approximation, I quickly just want you to take a look at this slide, because here's just a very short comparison of DFT, Hartree-Fock, and GW. That's basically just summarize what I just said. So basically that we kind of make the self-energy or the effective potential more and more complicated, and it has a more and more complicated dependence on the quantity which we use to construct it. So I also said something about the band structure. I think I took this over from a talk about the solid state. Well, anyways, so why does the GW approximation work that well? And actually, only like a month ago or so, I wrote a paper on that together with Fabienne Bruneval. It's on the archive now. And we basically wanted actually to figure that out. I mean, it seems like a reasonable question to ask. Everyone's using it. Why does it actually work? Of course, people have thought about it before us, but we kind of thought we make it quantitative. So what did we do? I go a couple slides back. We simply did this. We, instead of just doing GW, so again, this is just the first term in sigma and the first term in P, we actually also implemented the second term in sigma and the second term in P. And we wanted to see what happens. It's a little bit numerically involved, but basically the whole idea is that we wanted to see that those terms cancel. And you see it's not like always exactly the case, but here what you see in this plot is, you see some orange bars and some blue bars, and then you see some red rectangles, which are just always the sums of the orange and the blue bars. And you see that typically they just go in the different direction, the orange and the blue bars, which means for the red rectangle, well, that it's smaller than the individual contributions. In other words, if we add higher order terms to the self-energy and to the polarizability, the effect cancels. And on average, you see this here on the right. The effect for the polarizability is maybe relatively small. The one for the self-energy is bigger, but they come on average as opposite signs. So on average, the next terms after GW in the self-energy and after the second order term in the polarizability, they don't contribute much. So that was actually quite nice of a result. All right, I'll skip this slide. I will talk about neutral excitations, but that is just a bit of blah blah. But essentially, it just tells us that okay, we get neutral excitations from this quantity, which is a so-called some people call it a two-particle Green's function, but strictly speaking, it's not exactly a two-particle Green's function because a part is missing. And we can calculate this L, and then we get neutral excitations. Okay, let's do a little bit of let's say practical things. So the most difficult part of this talk is done, so I'm done with the equations. Well, not quite. There are a few more, but what I want to say is that in practice, GW calculations are rarely performed self-consistently. What we typically do is we do a neat trick. In the Dyson equation, to the GW self-energy, we add and subtract a Kohn-Sham exchange correlation potential. And then that's a general thing about Dyson equations. Whenever we have, let's say, a kernel, or the self-energy that's sometimes called a kernel for the Dyson equation, so basically a term in parentheses, whenever we have such a kernel, we can split it. So what we do, we basically first calculate the first Dyson equation, just with the exchange correlation potential, which is just DFT. So we do a DFT calculation, and then afterwards, we calculate a second Dyson equation with the kernel sigma xc minus vxc. Of course, we have to subtract the vxc because we don't want to double count. The second one, we can also write a single particle equation. So we end up with something like this here. And then we make, that's a crucial step, an approximation. We just say that the DFT orbitals are in practice so similar to the GW orbitals that we can neglect them. In other words, we just neglect all of the off-diagonal elements. Okay? What we then get is essentially just a shift. So this is a Kohn-Sham eigenvalue, and then this equation tells us, take the Kohn-Sham eigenvalue, add the diagonal element of the GW self-energy, subtract the corresponding matrix elements of the Kohn-Sham potential, and you get a correction. We have to do this self-consistently because the left and the right side both depend on omega. But that's not a problem. As soon as you have the self-energy, this self-consistency is really not a problem. We will see later that this comes with a problem, and that's so-called starting point dependence problem. But we can overcome this with a construction where we kind of do this self-consistently, and that's the so-called quasi-particle self-consistent GW. Likewise, we can also get relatively easily working equations for the Bethe-Salpeter equation. Basically what we get, and that is that's all you need to know in practice, we get in the end kind of like a Casida-like problem, so that's a standard linear response problem, which is typically implemented in TD-DFT codes. So also in GW-BSE, like in the BSE part, in the end we kind of have to solve a TD-DFT-like equation, only that, let's say, the matrix elements A and B are different. But basically, when you implement this, you can use like the machinery of, let's say, DFT codes in practice. All right. I just want to talk a bit about what we did in AMS, because of course this talk is a bit dedicated to what we are doing here. So I would just like to say that we kind of started implementing this in 2020, and indeed, as Ole just said, it was the work of my PhD. So that's the first paper we published, and you see that together with Luke Fisher, and you see that it contains the word low order scaling. And you see also here on the right, so that was at this time my attempt to make a graphical abstract. I'm really not good at that. I think it took me like a day to make that. And well, you can judge for yourself. But the results are nice because we basically could show that we can just on really modest hardware, let's say 1 or 2 nodes on a, but not even modern nodes, we could do like GW calculation on several hundreds of atoms. That was great. And I think basically it's the fastest code which is around. And then later we extended this actually to quasi-particle self-consistent GW. And I will show you later why this is good. We are pretty much the only code who can do this fast. Then later, that was in 2022, we also extended this to the GW-BSE. And here you also see in the graphical abstract, by the way, so this one was made by a friend of mine within 5 minutes. So she's clearly better in that than I am. But what we did here, we basically calculated the excited states of a hexameric complex in the photosystem 2 reaction center. So about 2,000 electrons, 11,000 AOs. You see in less than 5 days on 64 cores. So that was a single node actually. I mean, 5 days sounds a lot maybe, but I mean, also if you do TD-DFT on that, and I think we calculated maybe like 20 excited states or so, you need to wait a considerable amount of time. So that's really not a piece of cake, but we could show that we can do this. All right. Maybe later on, was actually mostly work by Eric van Lente, who implemented the whole thing into two-component formalism. Because of course, ADF, band, etc. are very strong in treating relativistic effects. So we wanted to be able to do that as well at the GW-BSE level. All right. Now I want to show just one slide about how accurate is it actually. And here, what I'm showing you are some results for organic acceptor molecule. There's like a standard set in the field. These are like 24 small, let's say, organic molecules. Think, I don't know, anthracene, body pie, I don't know, dinitrobenzonitrile, stuff like that. So relatively small, but I mean, let's say they're meaningful for photovoltaic applications. And then, of course, we want to calculate ionization potentials, electron affinities, and also fundamental gaps, which you see on the left, in the middle, on the right, respectively. This is actually from a paper I'm currently writing. So ignore the blue dots. So that's the best, but that's kind of like an approximation beyond GW. Let's say, we are developing also together with Fabienne. But important part are the red dots. So you see that GW. So that's just GW at RPA. So let's just say that's GW. Gives you a mean absolute deviation of 130 millieV for IP, a little bit worse for electron affinities, and also 120 millieV for the fundamental gaps, compared to delta CCSDT. I collected a couple of results below in the table, and you see lots of different GW approaches. And you see they are doing like, they have like fancy acronyms that typically means, okay, what is the starting point, etc. And but you see basically, for instance, here that you can get, let's say, mean absolute deviations of below 100 millieV for both ionization potentials and electron affinities. And you might compare this, for instance, to ADC3, which is quite an involved wave function-based method. And it actually doesn't do better. Well, okay, I would not interpret these small differences, but let's say we are at least on pair with that, maybe better, at much lower computational cost. So that's a good result. Okay, now a practical example. So in the following, I want to show you what do you have to do to get these good results as well. In practice with GW calculation, there are two pitfalls. And one is the already mentioned starting point dependence, and the other one is the slow convergence to the basis set limit. And I will tell you a little bit about what you can do to overcome these challenges or to approach these challenges. We will look at this molecule on the right, that's fumaronitrile. It's also in the set I mentioned below. It's pretty small, as you can see. It's 9 atoms, 5 carbons, 2 nitrogens, 2 hydrogens. So I did a couple of calculations on the system. And what you see on the left, so I have to explain this plot a bit. So what you see on the x-axis is the starting point. So what did I do? I did a G0 W0 calculation. So remember, that's the one where you do a DFT calculation, and then you get the quasi-particle energies as a perturbative correction to the results you get from there. And then I varied the amount of exact exchange in the starting point. So 0% would be PBE. So that's just GGA. 25% would be PBE 0, 50% would be, I don't know, I think there's also a functional with 50% on Lippic C, 100% would be Hartree-Fock plus GGA correlation. And then what I basically plot here on the left is the first neutral singlet excitation energy of fumaronitrile. All right. And now we basically can observe that depending on the starting point, we can get with G0 W0, so we're looking at the blue dots now, we can get an excitation energy of 4.8 eV if we like, or 5.8 EV if we like. That's of course great. So basically, if we know experiment, we can always get the right answer. But of course, that's not what was not very useful in practice. Okay, can we do better? So one option is to kind of iterate the eigenvalues, and that's much better. So you see like the green dots here, and that is almost a parallel line, because that's what we want. If the line is parallel, it means there's no starting point dependence. So parallel line is good. It's pretty good. And we can also do QSGW, and QSGW is formally completely starting point independent. And then you might, of course, ask, well, okay, but starting point independent, why is the line not completely flat? And that is pretty much just because I used here the default, the convergence criteria, and you basically get convergence within a couple of milli-electron volt, which is typically enough. But if you want to have it have a tighter convergence, you can do that, of course, as well. And then you get like a flat line. All right. So these are the things. That's the first singlet excitation energy. So what about quasi-particle energies? Same plot for the first ionization potential. G0 W0 ranges from, let's say, minus 11 or minus 10.8 to 11.8. Again, like a spread of one EV. EVGW now is also not a straight line anymore. We go from 11.4 to 11.8-ish. And QSGW again, approximately straight line. So basically, long story short, if you want to overcome the starting point dependence, QSGW is what you have to do. Of course, small issue here. We would, of course, like to reproduce the delta CCSDT result. So that's kind of like this line here, which is at 11.48 EV. Unfortunately, QSGW in this case overshoots it. That's too bad. It happens. For other systems, it performs better. And we also see that around 50% exact exchange in the starting point is actually kind of the sweet spot. So if you do a G0 W0 calculation, that's what I'm always recommending. Just take any functional. I always do PBE0, but you can also do B3lab if you like. It doesn't really matter. And set the amount of exact exchange to 50%. In most cases, let's say for organic chemistry, that's pretty much as good as you can do. But maybe if you go to larger molecules, this might change. So typically, the larger the molecule gets, the less exact exchange you need. And then, well, so then QSGW figured this out for you. So maybe that's better. Okay. So now we know what's a good starting point. Let's move on to the second issue, the conversion to the basis set limit. It's slow. It's really slow. So if we just look at the ionization potential in G0 W0, and I show here on the x-axis a basis set cardinality, double theta, triple theta, quadruple theta, quintuple theta, hextuple theta. No one wants to do a quintuple and a hextuple theta calculation. We also don't really want to do quadruple theta calculations. So we're always happy to get away with double, triple theta. That's, by the way, I would like to say that I did these calculations. I mean, you might be wondering, okay, what basis sets are these? These are not in ADF, and actually these are Dunning, correlation consistent Gaussian type basis sets. We can run these calculations as band, because in band we're using numerical atomic orbitals. So now in band we can also use Gaussian since recently. That's work by Pierre and Eduardo, who work at SCM. And that's very useful for benchmarking. So basically, I just took these basis sets and, well, and did these calculations for the first ionization potential, electron affinity, and the gap. What you see for the ionization potential, if you do double theta, you get 11.8. And you are pretty much almost, well, you want to go to 11.6. So almost 1 EV basis set error. Also at triple theta, you are kind of far off. And you kind of have to go kind of to maybe even quintuple theta to get a reasonable result, to converge reasonably. That's a problem, and for the electron affinity, it's actually even worse. So electron affinities typically converge even slower. We are, of course, in luck when we look at the gap, because here the errors for ionization potential and electron affinity compensate. So they come with opposite sign, or they cancel. So here, let's say with triple theta, we get a gap of 10.3, and at hextuple theta, we get 11.2. So we are already converged at triple theta within, let's say, 0.1 eV. So that's, of course, nice. But if we really care about individual quasi-particle energies, that's a problem, because we will always make a basis set error in practice. So how can we overcome this? One strategy to do that is basis set limit extrapolation, and there's kind of like a relatively famous strategy which has been pioneered by Helgaker and Klopper in 1997. Basically what they're doing, they use this expression here. They did it for correlation energies, but you can also do it for quasi-particle energies. You take the ionization, let's say the quasi-particle energy, let's say the ionization potential at a certain basis set, for instance, triple theta. You multiply it with 3 to the power of 3. Then you take another one, for instance, quadruple theta, multiplies as 4 to the power of 3, and then you divide it by the respective denominator. And what you then get are these horizontal bars on the left. Unfortunately, there's a problem. If you do this extrapolation based on a double theta and triple theta result, you get a basis set limit of 11.4. Okay. If you do it on a triple and quadruple theta result, you get 11.55, and so on. And you basically get increasingly accurate. So basically, the larger your two basis sets are you use for the extrapolation, the better your estimate of the basis set limit. However, but from what you're seeing here, you kind of need to do at least a quadruple theta calculation to get a reasonable estimate. So that's a rule of thumb. If you have, like, say, double and triple theta, it won't be that great, your extrapolation. So you need quadruple theta. That's already great, because then we don't need to do quintuple and hextuple theta. But I also don't really like to do quadruple theta. Okay. Now, Fabien Bruneval had a great idea. So in 2020, he found that the basis set error correlates linearly with the logarithm of the kinetic energy. So if you think about it, if you have a kinetic energy which is very high, this means you kind of have a very localized orbital, and apparently you need a larger basis sets to represent this localized orbital accurately. That's, let's say, pretty much this idea, and empirically you could find that there's kind of like a reasonably good correlation, or these are like Pearson and Spearman correlation coefficients between the logarithm of the kinetic energy and the basis set error. I mean, it's of course not a straight line, but it's reasonably good, and it's only double theta. If we would do triple theta, then the remaining basis set error is smaller, and we actually the points will be more and more in a straight line. So already for double theta, it's quite good. And basically what he then did, he took a couple of hundred molecules, made the effort to actually really calculate them at the basis set limit, and he just did a fit. And it's as simple as this. So he basically parameterized for each basis, for a couple of basis sets, Gaussian basis sets, he found parameters A and B. And if you have parameters A and B, the only thing you need to do, you need a single quasi-particle energy with a single basis set, and you need to calculate the logarithm of the kinetic energy matrix elements. You get them for free when you do an SCF calculation, and you get the quasi-particle energy at the complete basis set limit. So the fit was done with linear regression. So it's a relatively simple model, which I always appreciate. So simple is good. And what do we get? Well, so on the left, I show you what I already showed you in the plots before. The ionization potential obtained at different basis sets, and then here the extrapolated ionization potentials are the one which have been obtained by, well, this Helgaker formula. On the right, however, we see now the result of the extrapolation when we use the fitted A and B parameters. And what you see, if I just do a double theta calculation, just a single double theta calculation, I extrapolate my ionization potential to 11.51. And that's great because hex triple theta gives me 11.53. And if I do triple theta, 11.52, quadruple theta, 11.53. So basically, what at least for this molecule, I just have to do a double theta calculation, use these parameters A and B, and my extrapolated ionization potential will be just on point. This is a bit of a fortuitous example. I mean, in practice, it might not be always that great at double theta. But with triple theta, we basically get pretty much to the complete basis set limit. Of course, this requires fitting, and actually work in progress at the moment is that we actually are fitting the parameters A and B for SDO basis sets. That's done by a PhD student in our group because we want to kind of go a little bit into data-driven strategies to kind of machine learn ionization potentials, electron affinities, etc. So what we need is accurate training data. And to get this accurate training data, we need to do a whole bunch of calculations at the basis set limit. So we have not really any other choice than actually to extrapolate. Otherwise, we will never get training, let's say, data sets which are large enough at the basis set limit. All right. We are almost done. I also realize I just talked for quite some time. So, but this will be short. Correlation energy for sigma functionals. So the idea is if I have a Green's function and a self energy, I can always get an exchange correlation energy. So that's an exact relation, which is always true. And I can also write this as TR is a trace, and I can also write this as a trace of the Coulomb potential with the density-density response. So the density-density response is given by a Dyson equation. That's also an equation we solve in TD-DFT. And if we just approximate this kernel with just the Hartree kernel, we get the so-called random phase approximation you might have heard of. It's relatively cheap. I mean, if you are used to methods like GW, it's cheap. If you're used to GGAs, it's expensive. But for me, I would say it's relatively cheap. You can do it for a couple of 100 or even 1,000 atoms if you like. And you get good correlation energies. So now Andreas Görling had the idea to kind of approximate the higher order contributions to the kernel using data-driven strategies. So basically the idea is we take the kernel, we take the Hartree kernel exactly, we take the exchange kernel exactly, and then the higher order terms, so kind of like the correlation kernels, they're just approximated in the Taylor expansion, and then basically we fit alpha and beta. That's the general idea. Technically, it's a little bit more involved, so this gets transformed a bit. But basically, what we do in practice, we do an RPA calculation. After we do an RPA calculation, we kind of diagonalize the RPA density response. So Görling has called the eigenvalues of that sigma. That's why the function is called sigma-functional. And then basically then it has to be parameterized. So basically we do RPA exactly, and everything else we kind of fit. And the idea is, since RPA is already great, we only need to fit a very, very small amount of the correlation energy, just like a small correction. And you get the same computational complexity. And I just want to show like a result, an average result here. And you see here basically some statistical average over the TKN55 database. If you don't know that database, it's compiled by the Grimme Group, has been compiled by the Grimme Group years ago, comprises around 1,500 data points, and well, people use it to kind of benchmark their density functional approximations. And you see the sigma functionals, you see here in the middle, well, they are the best. In this plot, of course, I mean, we are a bit biased because it's but I mean, there's not so much you can tweak. It's just like the truth. We just calculate the whole database, and that's what we get. We compared, of course, to RPA. It improves over RPA. We compared to a good range-separated hybrid. It improves a lot. We compared to a good double hybrid. Well, we are better. So, in other words, I recommend it. And actually, what we also did in this paper, we parameterized the sigma functional specifically for SDO-type basis sets in the way that they should be accurate also, let's say, for relatively small-ish triple theta SDO-type basis sets. Okay, I'm done. I want to acknowledge a couple of people. Of course, I want to acknowledge all of SCM. well, I didn't put them on the slides, unfortunately, but so I want to acknowledge Fabien. So that's a guy with whom I'm working on these vertex corrections beyond GW. He's works at the CRNIS, and that's lots of fun to work with him. I'm learning a lot. Want to acknowledge Luke Fisher, my PhD advisor and my current boss. Here at the theoretical chemistry department. Also on the right, it's Andreas Görling, with whom I had this very nice collaboration on the Sigma-functionals. And I want to leave you with my conclusions. Well, I want to show you again the photosystem 2 reaction center, where we calculated this. So we made this beautiful picture with the ADF GUI of, let's say, the first excited state. And I would just like to say that you can do that as well with AMS. You can calculate excited states of these systems with good accuracy at a decent computational cost. I would like to emphasize that quasi-particle self-consistent GW overcomes the starting point dependence, and that you can use this data-driven extrapolation to overcome the basis set dependence. And this will also be, so the second part is not in the release yet, but it will be in the next release of the Amsterdam modeling suite, if everything goes well, but it typically does. So I think I can promise that. And finally, Sigma-functionals. I would encourage you, if you're interested in accurate energetics, try them out. I think they are great. And with that, I'm done. So thank you all for listening for, well, 45 minutes. I always talk longer than I expect. And I'm open to answer all of your questions.